All right, I think I'm live. Okay, folks, it is Friday night. I am pre-recording your lesson for next week. So you guys are going to be watching this lesson on the day that you are not doing in-person class during the pandemic. And so because I don't have to wait for students to join my live session, I'm going to go ahead and just get started immediately. I just recorded my lesson for AP Physics C. As you know, we are looking at different types of experiments and using that to review physics. So for this week, we are going to review rotational dynamics. All right. And so rotational dynamics is a pretty big subject. It's also a tough area of physics. And so I'm going to start off by discussing rotational dynamics in the context of energy. Okay. And so one of the things we learned about was the idea of rotational kinetic energy. The formula for rotational kinetic energy was 1/2 I omega squared. So I is this thing called inertia, rotational inertia, and I is equal to the sum of mr squared. So where m is a mass that makes up the object, and then r is the distance of that part from the axis of rotation. Omega is the angular velocity. All right. Let me show you an experiment that we could do with rotational dynamics. Maybe we have a pulley. So here's the pulley. Okay, and this pulley is like on a table. All right. And here's the floor. We've got a mass. And the mass has a string that comes out the top and wraps around the pulley like that. Okay. And when we let the system go, the mass starts to drop, the pulley starts to spin. Okay. And we make a measurement of what is this. Now this mass is going to accelerate, so its speed is not constant. But the question is, what is the speed just before it hits the ground? Okay. And there are lots of things we could vary. We could vary the mass of this. We could vary the inertia of the pulley. But I'm going to say, well, what if we varied the initial height of the mass? Okay, and we'll say that the pulley has an inertia I. All right, so what is the theoretical relationship between these variables? Okay, height and velocity just before it hits the ground. Well, to figure that out, by the way, the system starts out at rest. So to figure that out, we are going to use conservation of energy. Initial energy equals final energy. Okay. The initial energy is the gravitational potential energy of this mass. Okay. So it's just mgh. Does the pulley also have gravitational potential energy? Yes, but the pulley is fixed in place, and so it doesn't go up or down. So its gravitational potential energy is irrelevant for this problem. Okay. Just before it hits the ground, the mass has kinetic energy. All right. But we also have another form of energy because as the mass falls, the pulley rotates. So the pulley also has rotational kinetic energy, like that. Okay? So that is, we have two forms of kinetic energy in this problem. Now, one of the things that you want to remember here is because there's a relationship between how far this mass drops and how many times the pulley turns. And the relationship is the following. It is that omega times r, where r is the radius of this pulley, is equal to the speed. So basically, what this says is the faster the mass is falling, the more rapidly the pulley is spinning. Okay? So we can take that and we can divide both sides by r, and we get omega is v over r. And we can plug that into that equation. So we have mgh equals 1/2 mv squared plus 1/2 I over r squared times v squared. All right. And then we have both of these terms have 1/2. So we can multiply both sides of this equation by 2. And then we're going to divide both sides of this equation by m. Okay. So when I do that, this cancels out, and I get 2gh equals 2gh equals v squared plus I over mr squared v squared. So then both of these terms have v squared, so I'm going to collect like terms. And then I'm going to divide both sides by this number, by this thing right here. And what I get, I'm going to write this over here just to save space, is 2gh over 1 plus I over mr squared is equal to v squared. Okay? So as I said, we're dropping this mass from different heights, and we're measuring its speed. Okay? So we've collected a data table of height versus speed. All right? But if we look at this equation, we're actually going to need to transform this data table. Okay? So I'll give you a second to think about what we want to graph versus what in order to make a line. Okay, so I'm going to give you about 10 seconds. Okay, so because I have v squared here and I have h here, I actually want to graph h versus v squared. Okay, so my graph is going to be h versus v squared, and I can see that if I graph h versus v squared, then v squared is acting like y, and h is acting like x, and the thing multiplying x is 2g over 1 plus I over mr squared. All right? And so that means that this is going to look like a straight line, and the slope of that straight line is theoretically the slope of that line is theoretically 2g over 1 plus I over mr squared. Okay? Now, as I said in previous lessons, usually friction plays a role in these types of problems, and so you end up getting a speed that is slightly smaller than what you would expect, and so probably you would get a slope that is smaller than the theoretical slope. Okay, so that's one example of an experiment you could do with rotational dynamics. So now that was just one part of rotational dynamics. So I'm going to also review some other parts of rotational dynamics. So in particular, we learned about torque. Okay. And torque is a twisting force. It's something that causes something to spin. The formula for torque is F perp times R. So we have to use trigonometry in order to calculate the perpendicular component of the force. And R is how far is the force applied from the axis of rotation. We also learned, and I mentioned this above, about rotational inertia, which is the sum over mr squared. And rotational inertia is basically, in the absence of friction, how difficult is it to start something rotating or stop something that is already rotating, okay? And then we had the whole apparatus of rotational kinematics. So we had delta theta, which was angular displacement. We had omega, which is change in angle over change in time. It's called the angular velocity. So it's the rate of spin. And then we also had alpha, which is the rate of change of angular velocity, and that is the angular acceleration. So how quickly is it spinning faster and faster, or how quickly is it slowing down? And so if the angular acceleration is constant, we have the equations of angular kinematics. The equations of angular kinematics are as follows. Delta theta equals omega naught times time plus 1/2 alpha t squared. Omega final equals omega initial plus alpha t. And omega final squared equals omega initial squared plus 2 alpha delta theta. Okay, so these equations relate how much it spins, how fast it's spinning, to time and angular acceleration. Now, there is an equation that brings all of these concepts together, and that is Newton's second law for rotations. Newton's second law for rotations says that the net torque is equal to the inertia times the angular acceleration. So that, notice how we have torque here, we have inertia here, we have angular acceleration here. So this equation pulls together all of the different concepts in rotational dynamics and puts it into one nice equation. So let me show you an experiment that we could do that would test out Newton's second law for rotation. All right. So what if we have, again, a pulley? And so a pulley is always secured in place. So it's fixed, I don't know, to a wall or something like that. And it has a string wrapped around it. Okay. And we apply a constant force on the end of that string. Okay. And let's suppose that this pulley has a radius r. Okay. And so what we could do is we could put a little mark on the side of the pulley, okay? And we could watch that mark. And we could see how much time does it take for the pulley to go around once, all right? So maybe the experiment we do is we apply some different forces on the end of the string, and we measure the time it takes to do its first rotation. Okay? Now, obviously, if you keep applying this force, it's going to start spinning faster and faster, and it's going to take less and less time to do each subsequent rotation because it's speeding up. So the first one is going to be the slowest one. Okay, so neither of these quantities is something from angular kinematics. So we have to convert these into quantities that are angular or rotational dynamics quantities, okay? So the first thing we can do is we can take the force and we can convert it to a torque, okay? We can convert it to a torque because torque is F perp times R, where R is the radius of the pulley, okay? So here's the force. We know the radius of the pulley. And see how the force is perpendicular to the line connecting the center of the pulley to where the force is applied. So that means that the torque is just going to be F times R. All right? Similarly, we can take the time and convert that into an angular acceleration. So let me show you how. And when I show you how, we're going to assume that the pulley starts at rest. Okay? So if the pulley starts at rest, we have this equation, this kinematics equation, which is delta theta equals omega naught t plus 1/2 alpha t squared. Because it starts at rest, omega naught is 0. Okay? So we have delta theta equals 1/2 alpha t squared. All right? So now if we measured the time to complete a full rotation means that delta theta is 2 pi. All right? Because angular displacement is measured in radians. So I can take this and I can solve for the angular acceleration. So the angular acceleration, I multiply by 2, I divide by t squared, and I get 4 pi over t squared. So I see how I can take my force and I can turn it into a torque, and I can take my time and turn it into an angular acceleration. So I can convert this data table to a torque versus angular acceleration data table. Now, according to Newton's second law for rotations, torque is I alpha. So what if I do a graph of torque on the vertical axis and angular acceleration on the horizontal axis? Well, that means that torque is acting like y, and angular acceleration is acting like x, and then the thing multiplying x is the slope, which is the inertia. So this graph should look like a straight line, and the slope is going to tell us the inertia of the pulley. Okay? So if you saw a straight line in the data that you collected, then if you saw a straight line in the data you collected, then that would be evidence for Newton's second law of rotations being true. Okay? So that's pretty much all of rotational dynamics, but there is one other concept that I wanted to remind you about, just in order to review. It's pretty tough to do experiments with angular momentum, but I just want to review the concept. So angular momentum is sort of like the amount of spinning. Okay, it's denoted by L, and the formula for angular momentum is I times omega. So I want to remind you of the analogy between rotational motion and linear motion. So we had linear momentum, which was P equals mv, and the equation for angular momentum is exactly the same. It's the same idea, right? Because the rotational version of velocity is angular velocity. The rotational version of mass is inertia, right? Because mass is how difficult is it to push something or to stop something that's already moving. Inertia is measuring how difficult it is to start rotating something or stop it rotating. Exact same idea. And then this is the angular version of momentum, angular momentum, okay? So it turns out that just like momentum is conserved, if there is no torque on the system, then angular momentum will also be conserved. So I omega is going to be a constant if the net torque on the system is equal to 0. Okay, so it's the amount of spinning. So if there's something that's changing the amount of spinning, the angular momentum is going to change. Oops, this should say torque net equals 0. Okay. So one of the ways that you would see this applied oftentimes is if you have something that's spinning. Okay, so for example, stars are spinning. All right, and so maybe this is a star, and maybe the star collapses into a black hole. Okay. So it becomes a black hole. And black holes are smaller than the stars that they began as. Okay, so if we look at the definition of inertia, inertia is sum over mr squared. So r, because the star shrunk into a black hole, r went down. And so as a result, the inertia also goes down. Okay? So going back to angular momentum, if the inertia goes down, but inertia times angular velocity has to be a constant, well, then that means that the angular velocity had to go up. Okay? So what that means is that when a star collapses, and all stars have at least a little bit of rotation, they collapse, and the amount of spinning goes up dramatically. So black holes are actually spinning very fast. Okay, I don't know how to even represent that. They're really spinning fast, around. Okay, and they're spinning, and actually they drag space-time around with them. So if you were falling into a black hole, you would actually start to spin with the black hole as you fell in towards it, because the black hole is actually pulling space-time around with it. It's pretty cool. All right, so that is a review of rotational dynamics and some experiments. And I see I have some viewers. Thank you for watching the lesson live. And I will see you in class next week, hopefully.